The presentation are the characteristics of solid-state reactions, combustion synthesis, Sol-Gel method, mechanosynthesis, and hydrothermal and solvothermal synthesis. Characteristics of solid-state reactions. These reactions are diffusion controlled, and this is the fixed first law of J equals to minus d dc by dx. Small particles size that are well mixed are needed to maximize the surface contact area. Tammans rule suggests a temperature of about two-thirds of the melting point of the lower melting reactant is needed to have reaction to occur in a reasonable time. And thorough grinding is necessary to achieve a homogeneous mixture of reactants. The number of crystallets in contact may be increased by pelletizing the powders using a hydraulic press. The reaction mixture is typically removed and reground to bring fresh surfaces in contact, which speeds up the reaction. Sample purity is typically examined using powder X-ray diffraction, and containers for the reaction must be able to withstand high temperatures and must be sufficiently inert to the reactants. And common crucibles are silicon, alumina, zirconia or magnesia. Platinum and silver are also used for some reactions. Now the combustion synthesis. Combustion synthesis is a self-propagating high temperature synthesis, SHS method, and combustion synthesis uses highly exothermic and even explosive reactions to maintain a self-propagating high temperature reaction. An example of SHS reaction is the Thermit process for the extraction of iron, like Fe23 plus 2Al, 2 form 2Fe plus Al23. Here on Fe23 acts as oxidizer and aluminum acts as fuel. Reactants are mixed here together, formed into the pellets and ignited at high temperatures, and temperatures up to 3000 Kelvin are maintained during the first reactions. Now the compounds prepared using combustion synthesis. We can prepare hydrides for hydrogen storage, the borides for abrasive and cutting tools like the TiB2, carbides for abrasive and cutting tools, nitrides for high strength heat resistant ceramics, oxides for high temperature superconductors, silicides for high temperature cutting elements. Now the Sol-Gel method, a concentrated solution or colloidal solution of the reactants, that is the sol is prepared and then further concentrated to form the gel. And the gel is heated then to form the product. A sol is a colloidal suspension of the particle in a liquid, and the gel is a semi-rigid solid in which the solvent is contained in a framework of material that is either colloidal or polymeric. A dispersal stage may involve oxides or hydroxides in water with a specific pH, so the solid particles remain in suspension rather than the PPT. The sol forms a gel by dehydrating or polymerizing, and the sol at last gets gel forms the product by heating to decompose the alkoxides or carbonates to give the oxide. And the time and temperature is reduced compared to the conventional methods. And now sol gel preparation of LiNBO3. The LiNBO3 may be prepared by the sol gel method by starting with lithium ethoxide and the niobium ethoxide, and each ethoxide may be dissolved in absolute ethanol and mixed. Additional of water leads to partial hydrolysis, giving the hydroxy alkoxide by the following reaction. Then hydroxy alkoxide condense to form a polymeric gel with metal oxygen metal links. Then LiNBO3 is formed when the gel is heated and the remaining ethanol and the water is evaporated, and any remaining ethyl the groups are pyrolyzed. Now the mechanosynthesis. In this synthesis, the reactants are reduced to nanometer size with the introduction of mechanical defects, and the mechanical energy during the reaction is converted to heat energy, and no heat is supplied from the outside. The products in the synthesis may be in the metastable state with high vacancy concentration and structural disorder. And a recent example is the formation of the Zn2SNO4, a nano-sized the particle obtained by mechanochemistry, and the grain codes have found to have the inverse final structure, whereas the grain outside so the Zn is an disorder and the deformed polyhedra. And this method is very much useful for the synthesis of nanomaterials which are cheap and energy very efficient. Now the hydrothermal and solvothermal synthesis. Hydrothermal synthesis involves the heating of the reactants in the water or steam at high pressure and high temperature, and here the water has two functions. It acts as a pressure transmitting medium and as a solvent. Now the hydrothermal method has also wide range of applications. For example, one the phase many phases can be prepared hydrothermally at much lower the temperatures than would be required for solid state reaction. For example, to produce the magneto-plumbyte phase that would require heating of the oxide components BaCO3 and alpha FeO3 at for example 1 to 50 degrees centigrade, but hydrothermally can be prepared at much lower the temperature. Another is the hydrothermal process can be used for the zeolite synthesis. It can also be used for the single crystal of quartz SiO2 synthesis. And solvothermal synthesis is similar to hydrothermal synthesis, but it uses supercritical solvent mixtures, and it defines an increased number of applications. For example, Li2 of current interest. And as a lithium battery cathode material was synthesized and phased the pure at 300 degrees centigrade and 38 MPa in the 5 minutes in the supercritical water ethanol mixtures. And I took references from solid state chemistry and its application, second edition, chapter 4 by Anthony R. Weston, and from this link. Thank you.